welcome back. So, let us continue the discussion on this turbulent combustion. So, where we are into the business is that different combustion system. So, you can see how we broadly classify the system, which we have discussed, that one of the thing is that either premix system or non-premix system or partially premix system. So, here we now concentrate more on the two of these and see premix flame or the system which could be either turbulent, and you see some of the examples here. So, is a spark ignition engine, gasoline engine which is turbulent, low NOx stationary gas turbine. If you look at the laminar, there are flat flame, Bunsen flame, which are the simple flames, which are the laminar flames. And when you come down to differences, so one of the important things of premix flame is they are quite efficient, and also not only that, they are the cleanest combustion that one can have, but at the same time, as I said or kept on saying these things, nothing comes as free of cost. This is also quite dangerous. And why it can be dangerous? Because we have already seen some example where instability actually triggers. Now, another side of it, non-premix flame, where this kind of problem may not be there, and this could be also laminar or turbulent in nature, where you have candle flame, radiant burner, wood fire, and these are aircraft engine, rocket motor, diesel engine, these are the things. So, this classification based on your fuel oxidizer mixing and the fluid motion, but at the same time when you look at the non-premixed or diffusion system, they are always stoichiometric. That means the reaction zone of the combustion takes place at the stoichiometric situation. They are obviously less clean. So, the problem of your emission becomes quite dominant here, and that is why one has to control. At the same time, they are less efficient, but obviously you get some benefit that also it is not that dangerous. So, that means controlling a premix flame is quite challenging compared to a non-premix flame. Non-premix flame or the control of a non-premix flame is not that straightforward as one can see. Now, this is again an image which clearly shows you have a simple diffusion flame, and this is a methane which is burning in here, and from this side you have a diffusion flame completely, and this side you go to premix system. That means from the diffusion slowly you go. So, that means in between there would be something partially premixed, and then you go to premixed system. And the important observation one can have, there is a flame structure, then shape, color. So, these are the differences or visible differences one can have as soon as you, and this yellowish line and all these things which represent that there are unburned situation. So, here premix system, it shows that you can have a clearly nice blue flame, that means everything is getting burned. Here there is a lot of unburned hydrocarbons or something is there, that is why you get this kind of a yellowish nature. Now, usual practice, you need to store your reactants separately for safety, but you may burn them in premix mode for performance and pollution, because as I said, your premix flames are quite efficient. So, that means you have better performance, and they are also not that emission is not that high in premix flame, but at the same time your device need fast mixing system. So, there are which are the issues which can lead to a problems which usually happens in LP system, that means lean premix system. One of one of the biggest problem is that it has a instability problem or flashback problem. So, if you see this kind of a, but there the question may come, why one would like to have a lean premix system. So, the lean premix system advantage is that it reduces the NOx rapidly with the flame temperature, and this is one of the schematic of that kind of a premix system, where air fuel is mixed and injected to the chamber under swelling condition, then secondary air comes through, tertiary comes through for. So, but the lean system has a problem of this, and this is another example where methane is actually added with different percentage of hydrogen, and you can see the upstream portion of the injector how the flame actually moves. So, there is a movement of flame, this is called flashback, or in this particular example you can see there are some waves which are generated and that will lead to some sort of a instability problem, that is called the combustion instability. So, one hand one can expect to have a lean premix system to have better performance, less pollution, but at the same time it will become more susceptible to flashback or instability, and if that kind of situation happens, this is one of the picture one can see what happens to the burner assembly. So, this is a one which is actually damaged, this is a new one can see. So, it is a nice looking burner setup, but because of this instability or flashback kind of things, this has been completely damaged. So, that is why control of premix flame or the handling of premix flame is not that easy, it has certain issues, it is quite dangerous too. Now, one can classify the things in a different ways also. So far we are making the classification based on the flow and how the mixing takes place, that means either premixed or non premixed mode. Now, apart from that, one can have a classification like unconfined flames, that means the flame is not confined within a chamber or something, or rather it is not kept within a confinement. So, you can have premix flame, laminar flame, and the other is the confined flames. But in regular practice, most of the practical systems they are confined, or either or recover heat or mechanical power. So, engines, so they are in that way nature. Now, some example of your confined and unconfined flame, this is the same example where you have a diffusion flame and you go to premix flame. So, this is the unconfined flame, that means the burner is exposed to the open air, and this is the image of a confined flame where combustion is taking place within the combustor wall. So, there are some differences. What are those? One of the biggest difference is the velocity field, which are quite different because density changes due to dilatation. So, that is one of the important difference between. Now, in a confined system you have walls, so heat transfer becomes quite important, because once you have a wall, then heat transfer and then the cooling of the wall, these issues will come into the picture. So, it is not that straightforward that if you have a confinement. So, one hand unconfined flames have some less challenges, but at the same time confined flame has certain other challenges. Another important aspect is that acoustics can become important and also induce combustion instabilities, which are dominating multiple present programs. So, that means people are now looking at this acoustics business in seriously, because in the most of the practical systems are confined in nature, and the confinement brings into some of these challenges. So, if we put everything together, so our topic of discussion would be in a broader sense turbulent combustion. So, we will look at both their basics and theoretical aspects along with the modeling aspect. So, that means when you look at these two, turbulent combustion with their modeling aspect, everything is requires theoretical discussion on the basic flame types, that means on laminar, premixed and non premixed flames, which we will do first. So, that means to do this, first discussion would be on laminar flames, and after laminar flames we will move to turbulent flame. So, before doing the turbulent flame, one has to make some discussion on turbulence. So, that is the whole point, but there are complexities in combustion also, and how do we look at it. So, there could be a different ways of complexities. Number 1, the complexities comes from the kinetics or the chemistry. If you have more detailed kinetics or you are burning a particular fuel which is really complicated, then that can be represented some thousand of reaction steps, then the chemistry can become a real issue. Then geometric complexity. So, the real life burners or combustors, they are having lot of small components. So, geometric complexity could be one of the features. There could be complexity due to flows. So, and the finally multi-scale issues. So, again just to give you a glimpse of that, simple candle burner which is one of the simplest burning system, and if you go in the growing complexity level in this direction, this is your gas turbine combustor. So, everything is sort of happening here. So, that is in a growing complexity situation, and you have lot of scale, lot of different physics, they are taking place in that particular combustor. Now, we look at some of these basic flames like 0 dimensional flames. So, here all variables vary with time. Okay. So, you have a fuel and air. So, one of the thing is that your temperature is, and you look at this is a function of temperature, and this is the reaction, I mean source term in temperature equation, and this is the species mass transfer equation, species mass transfer equation, and this is the source term or reaction source term, and this comes because of your multiple reaction steps. So, this is where your 0 dimensional means there is no geometric complexity, flow variables are only with time. So, that complexity is also not there, but the kinetics brings in the complexity here through this reaction. So, what are the important component here? Even if you look at a 0 dimensional flame where everything is PSR kind of model, that means perfectly stirred reactor kind of model. So, they vary only with time, fuel and air. So, one thing is the complexity comes due to kinetics, as I said, and the second thing is that now not only the kinetics, your kinetics is also connected with your temperature equation or the thermochemistry. So, these are the two important things even for a simple flame, they become quite important. Now, you can go to a steady 1D laminar flames, here variables vary with x only. So, that means no fluid mechanics, you have some sort of an, so air and fuel they are coming in, so you get an flame sitting there, and here one can write a momentum balance for rho u would be rho naught A x and rho v would be rho naught A r. A is a strain rate. So, it is only varying in one direction and one can write these things. So, in the previous case we have seen that even then there is, so that means the fuel and air they are coming in contact, there is a flame sitting here. So, kinetics will be there, thermochemistry or the kinetics and thermodynamics, the connectivity will be there. There will be one more important things which will now come into the picture is the transport, because now they are transported. So, that complexity. Now, we will see how things get complicated. Now, this is another laminar flame which one can see in your gas burner or regular laboratory scale burner, which is but multidimensional. So, here variables could depend on different direction, that means x, y or z. Now, the important things could be kinetics, then obviously your thermochemistry, transport. Now, when you talk about multidimensional, that means things will vary with x, y, z. another important behavior which will come into the picture is fluid mechanics. So, that means one after another physical process, when they get involved, it will make systems more complicated. Now, you come to a situation where you have a turbulent unconfined flame. Here things are transient in nature, at the same time they depend on all x, y, z. So, this is an turbulent flame in a laboratory scale. This is your real flame comes from an oil and gas industry, where refineries, you can see this kind of flame. Things which will be involved: kinetics, because the combustion is taking place, there is a transport process, there is a thermochemistry, fluid mechanics, because these are turbulent. Now, top of that, your turbulence will come into the picture. So, that will bring in some extra effort to be handled, or the scales. Then, since these flames are so turbulent and scales, there could be radiation, there would be huge radiative heat which will be emitted from these flames. And finally, so most of the times if you are burning hydrocarbon and all these things, there could be soot particles, which are the black particles. Now, you can see how things get complicated. As soon as you move to a laminar situation to a turbulent one, even unconfined flame is kind of involved with so many different processes which makes things complicated. Now, when you go to turbulent confined flame, this is an example of your gas turbine combustor. Here you have all this information: kinetics, transport, thermochemistry, fluid mechanics, turbulence, radiation. Soot depends on a particular mixture and fuel and what temperature or not, soot may arise or may not, but what could arise in a different kind of complexities. One is the acoustics, that means because of some of the instabilities this may trigger in, then heat transfer at the walls and all these things, and then finally because of the wall heat transfer there could be thermal loading on the combustor walls, liners and everywhere. So, those materials can also expose to some sort of a small deformation, where your fluid structure interaction will become also important. Fluid structure interaction. Now, implication for the models and different codes, you have so many parameters: kinetics, transport, thermochemistry, fluid mechanics, turbulence, radiation, acoustics, heat transfer, FSI. So, everything one has to be kind of handled. How one can handle that? So, one of the best code or the models for a real application are not always the best codes and models for individual problem. So, you may have everything incorporated in one particular model, but that could not be the best one for your application you want to deal with, but it is a good one for realistic situation. Then the limiting part of the code would be the weakest element of all of them, especially for real application. So, one has to identify the weakest element. Now, depending on the expertise, one can see the weakest link at different places, and accordingly he has to or she has to resolve those things. So, which gives you an idea why this combustion process is so complicated, because it involved so many processes at the same time, and once you have so many processes which are involved at the same time, then things become really complicated. So, these are the complexities of combustion and that we need to handle. Complexities in combustion. And now we will start with some of the basic things like combustion and thermochemistry. So, we will develop our discussion or continue our discussion on the basic stuff, then we will make it go into the detailed discussion of the complicated things. So, what we will cover here? We will look at the basic property, then looking at the first law of the thermodynamics, enthalpy and some of the basic properties of flame and all these things, then finally chemical equilibrium. So, these things we will look at it. So, we can look at this, these are the already, you should have some background on thermodynamics, or some basics of combustion. So, you must know there are the property relations, there are extensive properties and the intensive properties. So, the extensive properties depends on amount of substance which are considered, for example, volume, total internal energy, total enthalpy, these are the example, and intensive properties which are expressed per amount of unit mass. So, for example, specific volume, specific enthalpy and all these things. Then your intensive properties also you can are temperature and pressure, and extensive properties are related to intensive one by amount of mass. So, for example, small mass into specific volume will give you total volume, mass into specific enthalpy will give you total enthalpy. So, they are sort of connected, the intensive properties and the extensive properties. So, one can look at it. Now, the other thing which we have already looked at is the required is equation of state. So, most of the time unless or otherwise it specified, we will be dealing with the ideal gas behavior. So, this will give you a relationship between pressure, density, temperature. So, an ideal gas behavior is that what it tells you that intermolecular forces and volumes are ignored. So, you can PV equals to N or universal constant T. So, one can say this is our equation. Then PV equals to, you can write in different terms. So, P small v is RT, P equals to rho RT. So, these are different form one can write the ideal gas law or the equation of state, and we can use in different form. Now, there is a specific constant which is the universal gas constant, Ru is or rather R is Ru by molecular weight, which is nothing but 8.314 kilojoule per kilomole Kelvin. Okay. And Mw is the molecular weight, So, most of the things that we will show in throughout our lectures will mostly deal with the gaseous state. So, we will require this gas law and we will be using this the different gas constant. So, somewhere we can use this Ru or R naught, whatever it is. So, that is what we use throughout this discussion. Now, there will be another thing which one can write is the calorific equation of state. So, the calorific equation of state which essentially relates the enthalpy and the internal energy to pressure and temperature. So, your internal energy will become the function of temperature and specific volume, and H becomes function of pressure and temperature. So, these are my number. Now, once we differentiate these two equations 1.4a and 1.4b, so we get du equals to del u by del t at dt plus del u by del v dv. So, this is 5a, and dH equals to del h by del t at dt plus del h by del p dp, which is 1.5 b. So, once you do the differentiation, then you get this. Now, 1.5a and 1.5b, you can write Cv equals to del u by del t at b, which is 1.6a, and Cp is del h by del t p, which is 1.6b. Now, for ideal gas, so for ideal gas, del u by del v at constant temperature is 0 and del h by del p at constant temperature is also 0. Now, we integrate equation 1.5 and put in 1.6. So, that will get us u as a function of T equals to u rep plus T ref to T Cv dt, which is 1.7a, and H T equals to H ref plus T ref to T Cp dt 1.7 b. So, here we have some reference. So, ref stand for some reference state, and we will define that reference state as we go along. Now, what for both real and ideal gases, the specific heats which are Cv and Cp, they are generally function of temperature. Now, internal energy of a molecule, there are how one can look at it. These are essentially the translation energy or vibration energy or rotational and temperature dependent. Monoatomic spacing, only translation energy would be involved. If it is diatomic or triatomic, all three like translation, vibration and rotational energy will be involved. So, more complex the molecule, the greater is the molar specific heat. So, now if you go to the ideal gas mixture and we will find out is the mole fraction, which would be Ni divided by on summation of J, which is Ni by N total, and mass fraction for ith species would be Mi summation over J Mj, which is Mi by M total. Now, for this ideal gas situation, for the looking at the mole fraction and mass fraction, one can find out that summation of xi is always 1 and summation of yi is always 1. So, these are the two important properties what one can 1.10 a and b equation number, and relationship between x and y, my yi one can write xi molecular weight I by molecular weight of the mixture, which is 1.11 a, and at the same time xi equals to molecular weight of the mixture divided by molecular weight of the I, which is 11 b. Now, how we define the molecular weight, mixture molecular weight, MW mix would be summation of I xi MWI, and MW mix is 1 by summation of I yi by MWI. So, total pressure one can find out, it would be summation of Pi. So, this would be 1.12 a, b and 1.13. So, we will stop here and we will actually continue in the next lecture.